Welcome to This Explainer. Today, we're diving into the literal nuts and bolts of robotic movement. We're going to take those abstract electrical concepts and turn them into real, tangible mechanical action. If you've ever stared at a complex machine and thought, how does a tiny spark of electricity actually make this whole thing move? Well, you are in the exact right place. We are building this up from scratch. Okay, let's dive right into this. I want you to picture two radically different machines. On one side, you've got this massive, heavy-duty robotic arm, the kind you'd see on a factory line, just effortlessly hoisting an entire car chassis into the air. And on the other side, a tiny vibrating bug bot that just kind of skitters and buzzes around on your desk. Now, these seem completely unrelated, right? But here's the wild part. They use the exact same raw electricity to do their jobs. So how on earth does identical energy power such wildly different actions? How do we get from a simple battery to either lifting a whole car or just vibrating a toy? That is the exact puzzle we're going to solve today. So here's our roadmap for the explainer today. First, the spark of motion. Then we'll compare DC and servo motors. Third, the electronic pathway. Fourth, we'll look at gears, wheels, tracks, and legs. And finally, your robotic design challenge. All right, kicking things off with Section 1, the spark of motion, turning energy into action. Take a second to really think about this. Why does a wall clock need a completely different kind of motor than, say, a remote-controlled car? On the surface, they both just use moving mechanical parts, right? But think about what they're actually doing. A clock needs this incredibly precise, slow, measured ticking. It has to move at exact intervals, all day, every day. But an RC car, that thing needs rapid, explosive power to just tear across the living room floor. You obviously couldn't use a clock motor in a race car, and no way would you want an RC motor spinning the hands of your clock at top speed. It's a great reminder that different jobs absolutely require fundamentally different mechanical hearts. Which brings us right to Section 2, DC versus servo motors, the core of movement. Now, as a builder, you'll see a huge distinction between your two main types of robotic muscles. First step, the DC motor. This one is all about continuous motion and rotation. If you want a wheel to just keep spinning and driving you forward, you use a standard DC motor. Simple as that. But then we have the servo motor. A servo doesn't just spin wildly in circles forever. It's built for exact positional control. It's meant to make a precise 90-degree turn or hold a mechanical arm at a very specific angle. So one is for endless spinning and the other is for exact measured positioning. And hey, this isn't just theory for tiny desktop hobby kits. Our sources highlight a really cool real-world application from an engineer named Jeremy Fielding. He actually took massive industrial motors and reconstructed them to build powerful, custom robotic arms. It's a total game changer when you realize this. By mastering these exact same basic principles, knowing when to use that continuous DC motor and when to use a precise servo, engineers like Jeremy can scale up from a weekend garage project to massive industrial-grade applications that literally do the heavy lifting. So, quick quiz for you. Think about the steering wheel on a car. What motor type does it actually need to work? Well, if you guessed a servo motor, you hit the nail on the head. A steering wheel absolutely needs that precise positional control to hold a turn at an exact angle and then safely return right back to the center. It definitely does not spin continuously in one direction forever. If you used a basic DC motor for steering, well, that would be a terrible and honestly pretty dangerous choice. Let's move on to Section 3, the electronic pathway, safe power delivery. Okay, big misconception alert right here. There is this super common belief that you can just wire a motor straight to a battery and it'll happily spin forever, just sipping electricity. Yeah, that is completely false. If you just dump raw power directly into a hardworking motor, things are going to overheat incredibly fast. They absolutely need a middleman. We call this component a driver, and it manages that power safely. Without a motor driver, you're running a very real risk of overheating your parts and, quite literally, melting your hardware right there on the table. So, let's walk through this crucial sequence step by step. Step 1 is your battery. That's where all your raw, untapped electrical energy lives. But remember, we do not go straight to the motor. The electricity flows to Step 2, the motor driver. You can think of the driver like a traffic cop or the brain of the power system. It regulates exactly how much voltage and current gets through at any given second. Only after it's been properly regulated does that safe, managed power flow into Step 3, the motor itself, generating the actual motion we want, safely. Let's look at how a standard robotic build actually evolves in practice. First, you start with the simple stuff, basic DC motor wiring. You're establishing that electrical pathway from the battery through the driver and into the motor. Second, you start adding mechanical advantages. You pop a gear onto that DC motor to dramatically increase your torque, which is that twisting force that gives the robot the physical strength to push or pull weight. And then, step 3, you might level up the build by adding a servo motor for those precise 90-degree turns, maybe for some sophisticated steering or pointing a sensor.
Moving right along to section 4, gears, wheels, tracks, and legs, hitting the ground.
These options brilliantly illustrate the real-world trade-offs roboticists have to make. Let's break it down. If your robot is all about speed and mostly operates on nice, smooth surfaces, wheels are absolutely your best bet. They're fast, they're super efficient. But if you have to navigate mud, rubble, or really rough terrain, wheels are just going to get stuck. So you swap them for tracks. You trade away some of that top speed for grip and stability. And finally, if your robot needs to step over big obstacles or move through highly irregular environments, you got to go with legs. But keep in mind, choosing legs means you're taking on a massive amount of mechanical complexity just to coordinate all those moving joints. Okay, let's actually apply these mechanics. We're going to do a little guided practice and figure out how to calculate a robot's actual physical speed across the floor. So let's say our robot's wheel spins exactly 10 times per minute. That 10 is our motor RPM. To find the actual physical speed, it's super simple. You just multiply that RPM by the circumference of the wheel. I just love this because it highlights this beautiful, direct relationship between the unseen motor spinning inside the chassis and the actual physical distance your robot is traveling out in the real world. And that brings us to our final section, Section 5, your robotic design challenge. All right, here is a final reflection prompt to wrap things up. If you were handed the task of designing a robot specifically to climb a steep flight of stairs, would you use wheels or legs? And based on everything we've talked about today, what do you predict your biggest challenge would be? Are you going to struggle to generate enough raw torque from continuous DC motors? Or is the real headache going to be managing the highly complex positional control of servos for a bunch of walking legs? I'll leave you to ponder your own designs with that thought. Thanks so much for hanging out with me for this explainer. Keep building, keep learning, and keep engineering.